Hi everyone. So last time we talked about the exterior algebra, or alternatively wedge products of some module M. And one of the things that we had previously defined for tensor products is we had defined the notion of tensor products of homomorphisms. Analogously to that, we can define wedge products of homomorphisms. So analogously to tensor products of homomorphisms of modules, we can likewise define homomorphism. We can likewise define wedge products of homomorphisms. So to do this, let F be a homomorphism between two modules M and N. Then we define the kth wedge product, wedge Kf, from the kth wedge product of M to the kth wedge product of N by the following rule. So the kth wedge product of F on M1 wedge Mk equals F of M1 wedge F of Mk. And since the kth wedge product of M is generated by wedges of elements in M, this uniquely defines a homomorphism. So I should say for M1 to Mk in M. Okay, so suppose now that we apply this construction to a vector space. So suppose that V is a vector space with basis B given by E1 up to En. So it should be a vector space over a field with basis B, E1 up to En. Okay, so in particular, V has dimension N. So now, if we take the nth wedge product of V, we get a one-dimensional vector space with basis E1 wedge E2 wedge E3 up to En. Okay, so this is a special case of the example from last time. You can always find a basis for wedges of a vector space in terms of wedges of the basis where the indices are strictly increasing. And in the case where you wedge up to the dimension, the only way you can find n elements of the bases with indices strictly increasing is if the basis is E1 has just a single element, E1 wedge E2 up to En. Okay. So the nth wedge product of V is a one-dimensional vector space spanned by E1 wedge E2 up to En. It's a special case of the exercise from the end of last lecture. It's a special case from the exercise at end of previous lecture. So in particular, we can apply this to a linear map. So suppose V is some vector space of dimension n with basis e1 up to en as above, and let f from V to V be a linear map. Well, then the nth wedge product of f is now a linear map between two one-dimensional vector spaces. So it must be given by scalar multiplication. So this is a linear map. Between two one-dimensional vector spaces. Hence, it is given by scalar multiplication, i.e., if I apply the basis of the nth wedge product of V, that's namely, so it's spanned by the element E1 up to En, then the nth wedge product of F is, since the nth wedge product of V is spanned by this, it's got to be some scalar multiple of E1 up to En. A lambda, a scalar. So let's say that V is over a field F, then lambda is in F. Okay, so then you might ask, what is lambda? Right, so if I have some linear map between a vector space to itself, then I can take the nth wedge product, and this produces some scalar lambda. The nth wedge product is multiplication by some scalar lambda, and this lambda only depends on the linear map. So you've associated some scalar to a linear map, or equivalently, you've associated some scalar to some square matrix, and you can ask what that scalar is. The answer is that lambda is the determinant of F thought of as a matrix. So this gives yet another way of thinking about the determinant. And this is my favorite way. And if you take more math subjects, particularly more kind of abstract courses, you will see that this is kind of the nicest, most intrinsic and most natural way of thinking about the determinant. So this gives another way of thinking about the determinant. Hold on. Okay, gives another way to think about determinant. Okay, so let's prove that this lambda as above is the determinant of F thought of as a matrix. So theorem F V to V as above then the nth wedge product of F applied to some element V in the nth wedge product of V is equal to V multiplied by the determinant of the matrix of F in the basis B. So this is the matrix of F with respect to the basis B. Okay, so the nth wedge product applied to an element in the nth wedge product of V, there's only scalar multiples of the single element in that vector space. It's a one-dimensional vector space. And the nth wedge product of F just multiplies V by some scalar, the scalar being the determinant of the matrix of F with respect to B. So that's one way of thinking about or defining the determinant. Okay, let's prove this. Okay, so for any matrix A, let's write it in terms of its columns. A1 to AN, so take a square n by n matrix. Entries in the field F with columns A1 up to AN. For any such matrix, let FA be the associated linear map. So we have a one-to-one correspondence between linear maps in a basis B and matrices. So I could equivalently just define this FA. So i.e. FA is the matrix. So FA is the linear map which takes the ith element of the basis EI to A times 0, 1 in the ith place. Right, so if I have a matrix A, then the associated linear map is just a linear map which multiplies elements in the basis by A. So thinking of EI, the ith element, as being represented by a column vector with a 1 in the ith place and 0 elsewhere, then I will take EI to the element A times this, which is the element AI, right? So if I take A and multiply it by this column vector, I just get the ith column vector of A, and then this is some element in F to the N, which is isomorphic to V via B. So I'm thinking of column vectors as elements of V under the isomorphism given by B, namely the isomorphism 0, 1 in, let's say, the jth position goes to EJ. So by thinking of the elements EJ as corresponding to column vectors with 1 in the jth place, I can identify columns with elements of V, and under that isomorphism, FA is a linear map which takes EI, the ith element of the basis, to the ith column of A. Okay, so if I have some matrix with columns A1 up to AN, I look at the linear map which takes the basis elements to the columns of the matrix. And now, if I write E for F to the N, the column space, then we define a multilinear map Phi from E to the n to the nth wedge product of V, which is just isomorphic to F. So the isomorphism here is just the basis goes to 1. So let's define a multilinear map from E to the n to the nth wedge product of V by saying that I want to take some n-tuple of column vectors a1 up to an, thought of as columns of an n by n matrix. Phi will be the multilinear map acting on the columns, which takes n columns to the nth wedge product of the associated matrix, the nth wedge product of the linear map of the associated matrix A. Here A is A1, AN. Applied to the basis element of the nth wedge product of V. So I'm defining a multilinear map by saying basically that I want to take some matrix to the nth wedge product of the linear map associated to the matrix. And the claim that we want is that this is the determinant map. So what we want is that phi is the determinant map, at least if I think of the target. So the target of phi is the nth wedge product of V. But if I identify this with the space of scalars F, then I want to say that phi is the determinant map. And we know that the determinant map is the unique alternating multilinear map which takes value 1 on the identity matrix. So it's enough to show that phi is alternating and phi of the identity matrix equals 1. Because we proved that the determinant was the unique multilinear map with those properties that it's alternating and it takes the identity matrix to 1. Okay, so let's prove first of all that phi is alternating. Okay, so let's try and kind of expand out what phi is. So phi applied to A1 up to AN is the nth wedge product of the matrix of A applied to E1 up to En. Now by definition, this is just Fa of E1, wedge Fa of E2, wedge Fa of En. And we already know that this is the column A1, wedge the column A2, wedge column AN, thinking of the columns as elements in F to the N. And this here is some element in F. Okay, so that is what... So now we've expanded out the definition of phi, and we're thinking of it as some function of the columns. So we've just shown phi A1 up to AN is A1 wedge A2 wedge AN in F. But this is alternating because X wedge Y is minus Y wedge X. So this is alternating. Since X. So this is alternating by the fact that the wedge product is alternating. Okay, and the second claim that we need is that phi of the identity is 1. well, so phi applied to the identity matrix is in the formula from the previous claim. This is or well, under the isomorphism, so thinking of these guys as elements, so these are all elements of f to the n isomorphic to v. So if I want to think, so I can think of these as the elements corresponding to E1, wedge E2, wedge En. So this is just the element in the nth wedge product of V isomorphic to F. So this is telling us that phi E1 this is telling us that that phi E1 En equals 1 times E1 up to En, which is the element which is sent to 1 in F. So which gets moved to 1 in F. So this tells us that phi takes the identity to the scalar 1 in F. Okay. Okay, so since we know that the determinant is the unique alternating multilinear map taking the value 1 on the identity, that tells us that the nth wedge product of the linear map must in fact be the determinant. So in conclusion, we get this little result here telling us that the nth wedge product of some linear map is scalar multiplication by some scalar, where that scalar is just the determinant of the associated matrix. So in other words, you can define the determinant basically as the nth wedge product of a linear map. So thinking of a matrix in terms of a linear map, the determinant of that matrix will be the nth wedge product of the linear map, where n is the dimension of the vector space. Okay, so this actually turns out to be a very nice way of thinking about determinants. Okay, so I'm going to end the topic of wedge products and determinants here, but I will give you lots of practice in the exercises for this week. Okay, so that ends the topic of matrices, and now we've done modules, and we've done matrices, which are 2 of the 3 main topics for this course. So now we move on to the last topic of the course, which is going to be Galois theory. And today we're just going to start with some very basic definitions. Okay. Okay, field extensions. So let's, so we're basically gonna, for the rest of today's lecture, just say some basic things about fields. So let's start with the definition. Suppose F and K are 2 fields and K contains F, or F is contained in K, then we say that F is a subfield of K and K is an extension of F. And K, let's call it an extension field of F. Okay, so some very simple examples. The rationals are a subfield of the reals. So the reals are an extension of the rationals. Another simple example, the complex numbers are an extension field of the rationals or of the reals. Okay, so to get kind of more interesting examples, we should recall a few different ways to construct fields. So let me say 2 different ways to construct fields. Construction 1 will be via quotients by maximal ideals. Okay, so let me remind you what a maximal ideal is. That's something that we've encountered so far in the midterm. Definition. Let M be an ideal in a ring R. Then we say that the ideal M is maximal if firstly M is not the entire ring R, and for any ideal which contains M, so for any ideal which contains M, then either I equals M or I is everything. So in other words, an ideal is maximal if the only ideal which contains it, well, are the obvious ones, M and R. So basically no proper ideal different to M contains M. So it's maximal in the sense that there's no bigger ideals other than the trivial ideal R. Okay. So let me remind you about a proposition which we essentially proved in the midterm, although the midterm was actually a special case. So proposition, let R be a PID and P a prime element, then the ideal generated by P is maximal. Okay, proof. Suppose I is some ideal containing the ideal P. Well, R is a PID. So since R is a PID, I is generated by some element Q. But P certainly lies in the ideal generated by P, which lies in the ideal I. So P is an element of I, and hence P lies in I is generated by Q, so P is some multiple of Q. Okay, but P is prime. And hence irreducible. And P equals RQ. So either R is a unit in which case Q is associated with P, or Q is a unit. But in the first case, where Q is associated with P, then they just differ by some unit, and then the ideals of P equals the ideal of Q, i.e. I, which is the ideal generated by Q, equals P. And in the second case, Q is a unit, so I is everything. Okay, hence P is maximal. So if I is an ideal containing it, we've just shown that it's either the ideal P or it's everything. Okay, so in particular, we know that prime elements in PIDs give us maximal ideals. And here's why those two things are useful. So proposition. Here, R is just any ring. Let M be maximal. Then the quotient of R by M is a field. So if I have a maximal ideal, then the quotient ring of R by M produces a field. Okay, let's prove this. So a field, right, to remind you, is a field is a ring in which all elements other than 0 are units. So R on M is a field if and only if X non-zero in R over M implies X is a unit, which is the same as saying that the ideal generated by X is equal to everything. So take some element A not equal to 0 in R over M, where A is in R. We need to show that the ideal generated by A is everything, because that will tell us that that for any non-zero element in R over M, the ideal of that non-zero element is everything, which is the same as saying that that element is a unit, which is so for any non-zero element is a unit, and hence R over M is a field. Okay, we need to show that A equals R over M. Okay, so to remind us, let's let Q going from R to R over M be the quotient map. It is, of course, surjective. Now let I be the inverse image of the ideal of A bar. In other words, so the inverse image of an ideal A bar, to remind you what that means all elements are in R, such that R bar, which is Q of R, is in A bar. Okay, so this gives you an ideal, since Q is a homomorphism. This is an ideal. It's an ideal in R. And furthermore, it contains M, just because for any element in M, Q takes it to 0. Since Q of little m equals 0, which is an element, of course, of A bar for little m in the ideal M. So if I take the inverse image of my ideal A, I get some ideal containing M. But M was maximal, so M is maximal, so either I is R or I is M, but I cannot be M because Q is surjective, and so by definition, since I is the inverse image of A, Q of I has to be A, since Q is surjective. So I can't be M because Q of I equals A, whereas Q of M is just 0, by what we just said. So I must be R. But then the ideal of A is Q of I, which is equal to Q of R. But since Q is surjective, the image of R is just R over M. Which means that the ideal generated by my non-zero element A is everything R over M. As desired, that was what we were trying to prove. Okay, so we've just proven that a quotient of a ring by a maximal ideal gives us a field. So let me just end today's class with an example of this construction. So the ring of integers is the prototypical example of a PID. If P is prime, then we know by what we've just shown that this gives us a maximal ideal. So the ideal generated by a prime is maximal. Hence the quotient is a field, Z quotiented by the ideal P is some field which we write as ZP. And since P becomes 0 in this is a field with P elements 0, 1, up to P minus 1. Okay, so we call this quotient ZP, and ZP is called the finite field with P elements. Okay, and maybe let me end this lecture very quickly with a second construction of fields. Okay, so one way of constructing fields, which gives us, for example, fields with P elements for P prime, is by quotienting by a maximal ideal. What's another way? Well, another way is just the field of fractions construction, which we've already seen. So let R be an integral domain. Then we previously constructed the field of fractions QR, which is just given by fractions A over B for B non-zero. So as an example, so this gives us a very useful way of constructing fields. So for example, let K be a field, then we have an integral domain Kx, polynomials in one coordinate x, and then we can define K parentheses x as the quotient field, the field of fractions of the polynomial ring Kx, and we call this the field of rational functions. So elements are rational functions, namely fractions of the form px divided by qx for px. So it's just a field of those rational functions, namely quotients px by qx, where px and qx are polynomials with q non-zero. Okay, so those are the two most useful ways of constructing fields, and both these constructions are very useful. Okay, so I'm going to end there. Thank you very much.